I so my topic for today, with some suggestions from Harry, was around the notion of rethinking wastewater treatment. And quite frankly, for the almost 30 years in which I've been working in this space, um, that is it's a realization that I came to maybe halfway into my career in the wastewater space, that there's a need for us to, quite frankly, rethink the way we approach water and wastewater treatment. A lot of the learnings that I've had is that this is one of those industries where we have responded to needs. So wastewater treatment, it doesn't matter where you are in the world. The remediation space is not a space where we had solutions and then applied those solutions to problems. In almost every case, we had problems and we were pushed to respond to those problems. I am reminded always that water and wastewater treatment is oftentimes not revenue generating. It is always a cost. There's always a cost to treatment, and therefore very few people are willing to act proactively. So oftentimes it is regulation that pushes us to do stuff. Oftentimes we don't act until the environment starts falling apart around us. But what I thought I would do today was basically to approach the conversation in five major areas. So the first one is I'll share some of the experiences that I've had in the water space. I think sharing that background will provide folks with the context for where I come from and the context for how I approach the water and wastewater treatment space, and probably also provide some good context for what has informed the positions that I take now about what it would take and what would be necessary in terms of how we rethink how we approach water treatment. I'll talk about some relevant fundamentals. I recognize that I'm talking to a group of experts, but I think sometimes it's also good for us to just level set and talk about some of these fundamentals. And simple as they might seem, I think it is those fundamentals also, the simplicity of the tools we have. We have a very complex problem, but the reality is there's a simplicity to how that treatment happens. It's mostly based on microbiology. It's microbes. It's simple. These are very simple organisms, but also very complex in the way that they behave. And there are many complex interactions that take place in the water space. And I think grounding ourselves in some of those fundamentals, at least in the way that I understand them, I think would be helpful. The idea of microbes and why that immense resource that nature has provided to us, how we can leverage that to better effect. Bioaugmentation, it's in the last decade of my activities, in the 3 decades that I've been in the water space, in the last 10 years of that experience, it's mostly been around this idea of bioaugmentation, the idea of tweaking what we have and leveraging our increasing knowledge of microbiology and how microbes behave to enhance what treatment units can do. Prior to this, the approach had always been that you had to engineer bigger solutions. There had to be more pumping and bigger systems and larger reactors. But once we understand what microbes do, there are things we could actually use those microbes for without really changing much about what that treatment space and that treatment environment looked like. And then I would share some thoughts about the future of water treatment, some of the work that we're doing in Optima Biome, and then we'll go into the Q&A session. So as I look over the last 20 to 30 years of my involvement in the space, there are, I think, 5 big areas of engagement and activity that have shaped my approach to water. Mary was gracious in our introduction. My background is in chemical engineering. I studied photochemical reactor design and engineering in Cambridge, mostly focused on water treatment, basically taking industrial wastewater, in this case, nuclear wastewater, and treating that. So that was my initial entry into the project. And the idea there was, how do we take things like UV light, readily available energy, and just leverage that for treatment to reduce cost, but also to allow us to deal with really challenging situations. Shortly after I left Cambridge, I joined a company called Praxair at the time. It's now part of a global industrial gas company called Linde. The manufacturer of industrial gas is obviously, when you're doing industrial research, what your employers want you to do is to take the products they manufacture and find applications for those in industry. And the major products we manufactured were things like oxygen. We made things like, manufacture things like CO2, and we were looking for applications. And when you make oxygen, the most obvious application is the aeration process in wastewater treatment. There's a lot of oxygen utilized by those microbes. And I spent quite a lot of time in Linde, Praxair, looking at things like oxygenation, a lot of work in industrial, wastewater, municipal wastewater treatment. Harry, you mentioned about 30-something plus billion liters a day. In the US, we treat 40 billion gallons a day of sewage, of municipal. That's just municipal. There's another almost 20 billion that is uniquely industrial. And then there's even more agricultural water usage that is completely outside of the numbers that I've mentioned. So it's an enormous, incredible amount of water that is utilized. But my experience in Linde Praxair exposed me to a significant number of technologies, a significant number of spaces, the immense challenges of water treatment, the challenges that increasing regulation brings to bear, and then, obviously processes like digestion, and the fact that in almost every situation, we're dealing with fundamental mass transfer issues. If you think about a typical wastewater treatment plant, there's the microbes themselves and just the mass transfer challenges of getting the organic material that these microbes are going to degrade to the microbe. You need, efficient mass transfer processes to make that happen. But at the same time, if you're using things like oxygen, you need to make sure that those molecules are getting to those microbes. So it's an immense mass transport problem. I also had the good fortune of being involved with a company called Hydromantis. I led their operations in the US. This is one of, I think, 2 companies in the world that are leading that are at the forefront of the application of mechanistic models in the water and wastewater treatment space. They have a platform called, they have several platforms that are utilized for biokinetic process modeling. They do freight and transport, what happens to not just broad things like COD, which are the high-level terms we use to track what's happening with organic materials, but they go down to the level of specific molecules, because there are some aspects of the regulatory process, especially here in the US, where the interest is not just in how much have you treated. The interest is also in what has happened to some specific organic compounds. So odor and air emissions, we looked at things like digital twin models and all of that. And as I said, in the last 10 years, my focus has been in bioaugmentation. I worked with a company called Drylet. And what Drylet does is basically bioremediation. How do you take microbes, go into existing systems without changing anything, without putting in more capital, without building more treatment footprint, without any additional pumping? How do you go into those systems with a keen understanding of microbiology and still find ways to optimize the processes? And in the last year, I have. Sorry?
I'm really sorry about this. One moment, please. Yeah. Please mute everybody. I'm very sorry about that, man.
No problem, no problem. Okay. And in the last year, I have, so for the last year, I've been, I run my own startup called Optima Biome. And what we do in Optima Biome is basically just leverage biology for bringing environmental and climate solutions. So in all of this time, this is just a selection of some of the types of processes that I've essentially worked with. So a lot of oxidative type processes, a lot of filtration, adsorption type systems, done a lot with oxygen, enhancing mass transfer, trying to improve mass transfer processes. We've worked with membrane filtration, with different types of biofilm systems, just to enhance, how you intensify biological processes. Conventional aeration, done, work with ozone, a lot of work with digestion. And as I indicated, one thing that has tied all these different processes together is just the modeling aspects. We have, I think we've come a really long way, and I'll talk more about this in future slides, where we now have a deeper, keener understanding of what is going on in these treatment processes. So if I jump straight into sewage treatment, the traditional approach we have to treating sewage is exactly almost about 110 years old now. It was developed by two gentlemen, Hardin and Lockett, based out of the UK in 1914. And the reality is the process has changed very little from what they did. The only changes, the major changes that have happened have been around what you do in secondary treatment. So for almost 60 years, so from about 1914 till about 1974, at least in the US, the exclusive focus of wastewater treatment was just removing COD. And if all you're trying to do is remove COD, so there are three major challenges we have in a wastewater system. We have carbon, we have nitrogen, we have phosphorus. And, we spent the first 60, 70 years just focused on removing carbon. If all you want to do is remove carbon, they're very, all we need to do very simply is capture about 50% of the carbon coming into a wastewater plant is in the form of solids, mostly fecal waste. So if we have grit removal systems that remove sand, if we have primary clarifiers, this is sufficient to remove about 50, 60% of your organic material. But if you're trying to remove nitrogen and phosphorus, that introduces additional complexities. And so most of the process changes that have happened in the last, especially in the last 20 years in the wastewater space, have been around developing, extending the process so that we can do things like nitrification, denitrification. We can do things like loxery, phosphorus removal, encourage the growth of phosphorus accumulating organisms and things like that. But the fundamental process has not changed that much. In almost every process, in every biological wastewater process, whether it's aerobic or anaerobic, you're going to generate sludge. What has happened that has changed in the last decade or so has been that in the past, we were all prepared to take the sludge and take it to a landfill. Now there's a recognition that locked up in that sludge is organic material, is energy, and there's no, why waste energy? Why take it to a landfill and have fugitive methane emissions, leachate result from that when you can actually tap into that energy source? The other thing that we've learned, and I'm grateful to have been part of this development in the last decade or so, has been that we now have a keener understanding of all the complex elements that go into the wastewater treatment process. As I indicated, I was fortunate to work with Hydromantis, leading their activities in the US. The CEO of Hydromantis is a gentleman who is actually now visiting family in India called Dr. Rajiv Goel. And, we have a keener understanding of the biokinetics that governs how microbes behave. We understand now that the thousands and thousands of microbes in a wastewater treatment process each have their own unique biokinetic rates. Some of them double every 2 hours, some of them double every 2 days. Somehow you have to find a way to balance those complexities. In some places, we're precipitating material. Sometimes we're using different chemicals. We're moving We're moving water that has solids, we're moving water that has biological solids that have a density that's close to that of water, but at the same time, that water, as it moves through a sewer, might actually also be moving sand and grit materials. And as you're moving through the process, some things are settling out, sometimes you're forming new solids. It's a complex system. But thankfully, we have been able to develop tools that allow us to handle that complexity, so that whether we're dealing with a plant that treats 1 billion gallons a day, like we have in the city of Chicago, or whether we're dealing with a small decentralized system that's supporting a school that has 400 people, there are now tools that we can use to basically design those systems to enable us understand precisely what they can do and how it can be done and what the footprint would be, and essentially what would be needed to get it done.